Hi everyone and welcome to the internet. What we're going to be doing in today's lesson is having a look at the concept of equilibrium position. So hopefully by the end of today's lesson we're going to be able to explain how changing different conditions is going to alter the equilibrium position. To start off though, we've got 4 questions based around our previous lesson which we did just before half term. So see if you can answer these 4 questions in your book for me. So I'm going to give you a few minutes to have a go at that. Okay, let's check our answers then. Obviously, tick any you got right. So, question 1, the symbol for a reversible reaction is, as you can see on the screen, half an arrow going right, half an arrow going left. If the forward reaction is endothermic, then the backward reaction would be exothermic, because remember they're opposites of one another. For question 3, the forward reaction would be N2 plus 3H2 makes 2NH3. and the backward reaction would be 2NH3 makes N2 plus 3H2, making sure obviously we've changed our reversible reaction arrow to a standard arrow. And then question 4, it's dynamic because the reactions are still occurring, but it's an equilibrium because the rates of the forward and back reaction are equal. So give yourself 1 mark for question 1, 1 mark for question 2. You can have 1 mark for the forward reaction and 1 mark for the backward reaction on question 3, and then a mark for saying that dynamic because the reactions are still recurring, and a mark for saying equilibrium because the rates of the forward and backward reaction are equal. So that gives you a total of 6 for today, so give yourself a score out of 6. So the first thing we really need to know then is, what on earth am I talking about when I use this phrase equilibrium position? Now, when we talk about the equilibrium position, what we're actually doing is describing the relative amounts of reactants and products at the point that we're at equilibrium in our reaction. So what we actually find is we can make statements as to if the position is on the left or on the right. So if we say the equilibrium position is on the left, then we've got a concentration of reactants greater than the concentration of products. Whereas if we say the equilibrium position is on the right, then that tells us the concentration of reactants is less than the concentration of products. So if you try and imagine it, kind of like a sliding scale, so you've got reactants on the left and products on the right, and then the equilibrium position is like this little marker that floats between them. So that if we've got a greater concentration of reactants, then the equilibrium position marker is going to be sliding towards the left. Whereas if we've got a greater concentration of the products, then it slides more towards the right. So make sure you've got those 3 points written in your book. I'll leave them up for a couple more minutes to give you a chance to get those written down. What we're going to do then is have a look at different conditions and how they actually impact on this equilibrium position. So the first one we're going to have a look at is the effect of pressure. So if we increase the pressure, then the equilibrium position moves in the direction of the fewest moles of gas. So that first sentence there is kind of the key point, if you like, about pressure. That's our little rule that we're going to follow, because as we hopefully know by now, chemistry is a lot of rules. So if you remember, if we increase the pressure, the equilibrium position moves in the direction of the fewest moles of gas, you're halfway to winning this bit. Now, what we've got in the second box on our screen is an example reaction. So it's a reversible reaction. Obviously we know that because of the reversible reaction sign we've got there. And what we start off with are 2 moles of our sulfur dioxide, which is reacting 1 mole of oxygen to make 2 moles of sulfur trioxide, SO3. So jot those points down for me first of all. When it comes to actually answering one of these questions then, if it was to ask us what would happen to the equilibrium position if the pressure was increased, and we're looking at our example equation here, then the first thing we need to do is identify the gases. So to do that, we look at the state symbols, which are those letters in brackets. Now in this case, we can see all 3 are gases because it's a G in brackets. Hopefully we remember our state symbols from our earlier chemistry topic. L is a liquid, S is a solid, G is a gas, and AQ is the aqueous solution. Now in this case, everything is a gas, so we need to look at it all. Once we've identified the gases, what we then do is we need to work out how many moles we have on the left, so our reactants, and how many moles we've got on the right, our products. So here we've got a 2 in front, so that means we've got 2 moles of our sulfur dioxide, and because there's no number in front of the oxygen, that means it's 1 mole, so we've got 2 plus 1, which gives us 3 moles on the left. Okay, so 2 moles of sulfur dioxide, 1 mole of oxygen, gives us 3 moles of gas in terms of the left hand side. On the right, we've got 2 moles of our sulfur trioxide, and then we come back to our little rule. If we increase the pressure, the equilibrium position moves in the direction of the fewest moles of gas. So 3 is bigger than 2, so that means the equilibrium position is moving towards the 2 moles, the fewer moles. So the way we answer that is we just say the equilibrium position moves to the right. And that's it. Obviously, if they were to ask you to explain, then you'd say the equilibrium position moves to the right because there are fewer moles of gas on the right compared to the left. And that's how we answer those questions. Okay, your turn. Here's another question based around pressure. So have a go at answering this in your books. I'll give you a couple of minutes to have a go. Let's mark that answer then. So, explain the effect on the equilibrium position of increasing the pressure in the reaction. And then we got CH4 plus H2O makes carbon monoxide CO and 3H2. So first thing we need to do is have a look at our state symbols. All of them are gases, so we're looking at everything. Then we work out the number of moles of gas on the left hand side, which in this case we've got 1 mole of CH4 and 1 mole of H2O. So 1 plus 1 is 2. And then we do the same on the right there. We've got 1 mole of carbon monoxide and 3 moles of hydrogen. So 1 plus 3 is 4 moles of gas. We can identify then that we've got the fewer moles of gas on the left hand side, 2 compared to 4. So when we're answering this, we need to say that the equilibrium position moves to the left when the pressure is increased, because the left has fewer moles of gas than on the right. So give yourself a mark if you worked out the number of moles of gas on the left, a second mark if you worked out the number of moles of gas on the right, and then your final mark for saying that the equilibrium position moves to the left. So give yourself a score out of 3. If you didn't get it right, I'd suggest you hit pause on the video now and then write the correct steps in so you hopefully can review this and understand how to get it right next time. The second type of condition we could alter is the concentration. And again, that top box is the important one. It's our rule for concentration. So make sure that stands out like we did with the pressure. If the concentration of a substance is increased, then the equilibrium position moves in a direction away from that substance. Now, what we've got again in that second box is our example. So we've got our lovely chemical equation there. And then we've got the question we could answer underneath. So I'll just give you a couple of minutes to jot that down and then we'll have a look at how we solve it. So if we read this question then, the concentration of sulfuric acid is increased, what happens to the equilibrium position? So first thing to do is find the sulfuric acid. And hopefully we remember that sulfuric acid is H2SO4, which is there on the left hand side. So that tells us that the sulfuric acid is increasing in concentration. So because if we've got one of our reactants increasing in concentration, the equilibrium position is going to be pushed to the right. So to answer what happens to the equilibrium position, we can say that the equilibrium position moves to the right. And that's it. Again, your turn to have a go at a question based around concentration. So questions on the screen. I'll give you a couple of minutes to have a go answering this in your books. Let's check that answer then. Hopefully we identified the fact that in the question it's telling us that the concentration of chloride ion, Cl-, is actually increasing. So if we actually look at our question, the chloride ions are on the right. We can see they're at the very end of that chemical equation. So if the concentration of chloride ions increases, the equilibrium position is going to move away from them. So because the chloride ions are on the right, the equilibrium position moves to the left. So give yourself a mark if you got that the equilibrium position moves to the left. The third and final condition we're going to look at is temperature. And again, our first box there is the important rule that we need to memorize. So if the temperature is increased, then the equilibrium position moves in the direction of the endothermic change. So whichever direction the endothermic change is going in, then our equilibrium position moves that way. Quick reminder for you on some of the work we did back in C3 on endothermic and exothermic reactions. If we have an exothermic reaction, then it's got a negative sign for the energy change, so it'll have a minus in front of that number. If it's an endothermic reaction, then it will be positive sign for the energy change. So what we can do there is just identify if we've got an endothermic or exothermic reaction just by looking at our energy change, or the delta H value. So what I've given you at the bottom is another example of a chemical reaction we could look at, and we can see the delta H is on the right hand side there. So again, I'll give you a couple of minutes just to jot these points down. If we have a look at our chemical equation down at the bottom here, then we're going to work out what's going to happen if we increase the temperature to the equilibrium position in this case. So the first thing we need to do is look at the energy change, so the delta H value. And in this case, it's minus 58 kilojoules per mole. So if it's a minus in front, then we know that that is an exothermic. So that one we know is exothermic, and that will be for the forward reaction. So hopefully we remember what we said earlier, that if our forward reaction is exothermic, then the backward reaction is going to be the opposite. So the backwards reaction, therefore, is going to be endothermic. Now, our rule is that if we increase the temperature, then the equilibrium position moves in the direction of the endothermic change, which is in the backwards reaction, which means that it's going to move left. So it moves to the left. And that's all we need to do to solve these ones. Your turn then. Have a go at answering this question in your books. Let's mark this one then. So if you identified the fact that the forward reaction is exothermic, give yourself a mark. And the reason we know that is obviously the delta H is negative. If you said that the backward reaction is endothermic, give yourself a second mark. And finally, if you said that the equilibrium position moves to the left when we increase the temperature, there's your third mark. So give yourself a mark out of 3 for this one. Final thing for today then is answering our plenary questions. So 3 questions for you to have a go at. Obviously, take your time to answer these. I'm going to leave them up for about 4 minutes today, but if you need any longer, just hit pause and take as long as you need.